Greetings, dear audience. My name is Stefan. I am Sales and Application Engineer for laser products at iC-HausVideo. In this hands-on video, I will go through the process of getting started with the iC-HT evaluation board. The iC-HT chip in the center of this board is a continuous wave driver with two channels to drive laser diodes. The iC-HT can be operated in ACC, automatic current control mode, or in APC, automatic power control mode. In the case of automatic power control, a photodiode is needed as feedback. For more details about the differences, see our Tech Talk, Understanding Control Concepts. The iC-HT has a serial interface to configure the parameters for the laser circuit. With these features, it can be used in applications where flexibility of adjusting the light power is important, or when it is useful to switch between different wavelengths, for example, in microscope lighting. This evaluation board, HT1D, simplifies laser control down to a neat graphical user interface. Let's have a look at the pieces that are needed for basic evaluation of the iC-HT's functionality. The HT1D comes with USB cable and a dummy for the laser circuit. This dummy has an infrared LED and a photodiode. So it replaces a laser diode with a photodiode integrated in its housing. From the iC-Haus website, the graphical user interface software HT1SO is needed. Always handy to read the input and output signals is an oscilloscope or at least a multimeter. With everything on the table, we can transition to a practical example. I decided to start with the simplest variant to get a current through the laser diode circuit. Automatic current control, ACC. Studying the datasheet of the iC-HT itself and the manual for the evaluation board, HT1D, should be part of your preparations. Drawing out the current path of the laser circuit and tracing the voltages from the configuration pins to their sources helps to set the required jumpers. To be able to minimize the power dissipation, the laser diode circuit will be supplied from an external lab power supply at the terminal VB-in at the top of the HT1D board. Here on this schematic, following VB-in to the laser diode, it becomes clear that jumper JP10 must be set accordingly. So jumper JP10 below the laser diode sockets for channel 1 goes onto its 1-2 position labeled VB. The iC-HT chip shall be powered with 5 volts from the USB. So JP12 goes in the top center of the PCB, goes onto its 1-2 position labeled USB. Important to know are 3 of the chip configuration jumpers which might prevent light output. JP1 should be closed so that the chip is active and not in standby. The output channels have to be activated by closing JP3 and JP4 respectively on a pin configuration level. In addition to the pin activation, the 2 channels will also have to be activated using the software GUI. Most of the other jumper settings can be taken from the HT1D manual. In section Interface Selection, there is a table for SPI operation to look them up. Each individual channel features a pair of sockets for connecting a 3-pin housed laser diode with integrated photodiode. The iC-HT can deal with 2 of common schemes how photodiode and laser diode are connected, with the 3 leads of their shared housing. Here you can see 2 sketches on the connectivity of the 2 supported schemes, the N-type and the M-type. The circuit diagram of your laser diode must match with either the N or M type. If your laser diode housing has only 2 leads, which indicates that there is no monitor diode, you can still operate it without feedback and a constant current in automatic current control mode. You can infer from the little drawings on the PCB or the numbering in the circuit description in which orientation to inlet those in the socket. The laser dummy that is included in the evaluation kit is an N-type, and this goes into the other socket, which is D1 for channel 1. The sockets for the exchangeable parts are not important for now, as we are going to exclusively use chip internal control. At the lab power supply, the voltage for the laser diode circuit needs to be set. I set this to 3 volts. That is the sum of the forward voltage or operational voltage of the laser diode plus 1 volt due to the saturation voltage of the iC-HT. Here, of course, it's the forward voltage of the dummy replacement. With the 3 volts from the power supply now connected to VB-in, it is now time to deal with the software installation. If you haven't, download the HT1SO GUI from the iC-Haus website. Please be reminded that you need to install 2 things from the zip file: the USB driver and the HT1SO GUI. After installation, I have plugged in the USB cable to the PC and the HT1D board. The small LED labeled N-check immediately lights up to indicate that the iC-HT is supplied with power, but is in a non-operational state. No wonder it needs to be told what to do. Time to start the HT1SO GUI and do so. At the time of recording, the HT1SO is at software version B3. The very first step is to connect the GUI with the iC-HT by clicking on the button labeled Interface. When a successful connection was established, its inscription changes to Connected with a green background. The iC-HT is currently in operation mode, but changes to the configuration can only be made when the chip is in configuration mode. The GUI makes our lives easy here, as long as the auto config mode is active. With that box checked, all the switching between operation and configuration happens automatically in the background. The setting up is done in the Configuration tab. Let's go into the Status Monitor tab first to see in which state the iC-HT started up. A click on Read Status updates the indicators with the values from the chip's status register. The 2 green lit indicators Power Down and RAM Initialized are a clear indication that this was the first read of the status register after power up. Also note that the error LED on the PCB is not lit up anymore after the status was read. If we repeat the readout by clicking Read Status again, the Power Down and RAM Initialized indicators get dark. Current state channel 1 and 2 are dark, indicating that both channels are currently turned off. We will activate channel 1 soon in the Configuration tab. As there are enable pins and jumpers on the evaluation board for the channels beside the digital control, there are 2 monitor status bits that tell us if a channel was active between now and the last time the status register was read. Now that we cleared the status error, we can go back into the Configuration tab and configure channel 1 for first test. The first thing will be to run the laser dummy with about 1/3 of its rated power, using the automatic current control. The laser dummy is rated for a maximum of 100 milliamps of current, so running it with approximately 30 milliamps will be a good start. See, changing the regulation control from APC to ACC results in a change of the control down here in the subject for calibration area. Before it was a voltage reference value, now it is a current reference. Please note that all the values in the different drop-downs of the GUI are subject to individual calibration of each iC-HT. The spread of their typical characteristics can be found in the iC-HT datasheet in section Electrical Characteristics. For finding accurate settings, a laser power meter should be used to measure the actual output of the laser diode. The current reference control displays a wide range of possible current settings. The lowest value that's currently selected is about 77 milliamps, and it goes all the way up to 850 milliamps, which is enough so that the specified maximum of 750 milliamps per channel can be reached with any device and setup. Unfortunately, the smallest value of 77 milliamps is more than the 30 milliamps that I would like to start with. Good that there is a low current checkbox. If this checkbox is activated, a different variable resistor is used inside the iC-HT. The current reference now goes from 9 milliamps to 100 milliamps, so the 30 milliamps for the laser dummy is possible to choose. The current limit is 127 milliamps, the highest possible value in the low current range. I cranked this down to 110 milliamps to be closer to the current rating of the laser dummy. The value of the internal resistor does not matter when ACC is used. All the important parameters, regulation mode, low current range, current limit, and the current reference were set. What is left to turn on the current? Remove the tick mark from the tick box Disable Channel. Now observe how the LED lights up on the IR-sensitive camera when the channel is enabled. Nice. Let's check what is in the status register by switching into the Status Monitor tab and read status. Now the two green indicators for channel 1 are lit. This indicates that everything is okay. Back to the configuration to see if the controls have an actual effect on the light output. So let's provoke an error to see how those must be handled. On this particular device, setting the current to approximately 100 milliamps triggers the current limit, which is set to approximately 110 milliamps. The check for error LED lit up and channel 1 was turned off. To re-enable the first channel, I have to lower the set current and reread the status register. That is all what is needed to operate the iC-HT with automatic current control. Now for the automatic power control mode. To configure it, disable the active channel. When I switch to regulation mode to APC, the reference control changes back to voltage reference. So let's have a look at the settings. The voltage reference still has its register value, the same hexadecimal value as it had during the ACC experiments. In APC, this should be around 500 millivolts, which is in the middle of its possible range, 100 to 1100 millivolts. The main parameter to set the output power in APC mode is the parameter RMD, the resistance value of the internal resistor. The higher the value, the lower the output power. Some fine-tuning of the output power can later be done with the voltage reference. So far, the RMD value was left untouched, so it is still at its startup value, hexadecimal FF, or approximately 407 kiloohm, which is its highest value. I will reduce it until I see current draw at the power supply of the laser circuit and can observe light output with the IR-sensitive camera. As the 407 kiloohms are a safe value, I can enable the channel again and start dialing it down. 200 kiloohm, 100 kiloohm, 80 kiloohm, 60, 40, 30, 20 kiloohm. Yes, there might be something, current is already flowing. 15 or 16 kiloohms, 10 kiloohms. Yeah, we are approaching it. Instead of dialing down slowly, you can of course derive a starting point for the RMD value from formulas and example calculations in the iC-HT datasheet and the photodiode characteristics found in your particular laser diodes datasheet. So here 6 kiloohms, yeah, 5 kiloohms, definitely something is visible or becoming visible, but here with the 2 kiloohms there is something. So let's go further down here. Now there's really light, and now I have 29 milliamps. So yeah, on this device I have to set around 600 kiloohms to reach the 30 milliamps that were approximately set during our ACC experiments. So this is now a coarse setting of the output power. For more fine-grained power setting, the voltage reference can be varied. Best practice for a stable control circuit is to stay within 400 to 600 millivolt. A higher value here increases the output power and a lower value decreases it. Just to have a quick look how the fine-tuning works, when set to 600 millivolts instead of the 500 millivolts, the current drawn increases to 35 milliamps. This will yield a significant power increase. Those were the basic steps you need to go through to set up a laser diode for automatic power control with the iC-HT evaluation board. More details, especially on the topics not covered in this video, like using external components instead of built-ins, can be found in the datasheet of the iC-HT and its evaluation board HT1D. All available from our website iC-HausVideo.com. So long and goodbye.